Alright, so here we basically just want to apply the previous theorem. So x has the normal distribution. So let's recall that the probability that x is less than or equal to a value x is the integral from negative infinity to x of 2 pi the minus 1/2 times the exponential of minus y squared over 2 dy. So here we're going to define things that were used in the previous exercise. So g of x is e to the x because that's a function that we're sending our random variable through. We're computing the exponential of the random variable x. And so the exponential function is just given by g. And then alpha and beta is sort of like the maximum range that g is increasing and differentiable on. And so certainly it's differentiable on the entire real line, so we just let alpha differentiable and increasing on the entire real line, so we just let alpha equal minus infinity and beta equal infinity. Okay. So what do we have? In order to in order to apply the exercise, we need to figure out, so we need g inverse of x. We need to compute this, and this is just the natural log of x. I'll put parentheses around it. G prime of x, well, that's just e to the x. Then we also need the lower and upper bounds of, or we need g inverse of alpha and g inverse of beta. So g inverse of alpha, well, I'm just going to write this as 0. Basically, this is not technically true. You can't take the inverse image of minus infinity, but the limit as x goes to infinity of g inverse of x is the limit as x goes to minus infinity of... Wait, what? No, as x goes to 0 from the right, g inverse of x goes to minus infinity. And so in that sense, this is true. And g inverse of infinity is going to be... So I'll put this equals in quotes. Because it's not technically true, but it's enough for what we need to do to answer this question. So g inverse of infinity is just going to be infinity. And so g of x equals exponential of x has density function given by which is supported on the interval g inverse alpha to g inverse beta, which is just 0 to infinity. So this is sort of why I'm not making a huge fuss about g inverse alpha and g inverse beta. I'm not making that much of a fuss because they're only used here to define the support of the density function. And the support of the density function doesn't have to be a bounded interval. It can be unbounded. That's completely fine here. I think more work is technically required in order to make this rigorous, but I don't know. I think it makes sense, or I don't think it's necessary. So let's see here. Let's look back at the previous exercise. Were there any? I'm looking back at the previous exercise, and I don't think it changes if we allow alpha and beta to take on values on the extended reals. Maybe there's some things you have to worry about, but I don't think so. Okay, so we have this. So it's supported here and is given by the formula. Now, this was mentioned in the previous exercise, but it looks like this. F of g inverse of x over g prime of g inverse of x. So this is going to be f of the natural log of x over e to the power of the natural log of x. So this is going to be, well, obviously we've got 1 over x because the exponential of natural log of x is just x. And now we have to multiply by f of natural log of x. And f is the function 2 pi to the minus 1/2 times the exponential of minus y squared over 2. So this is going to be, so we have 1 over x times 2 pi to the minus 1/2 the exponential of minus natural log of x squared over 2. So let's see here. Since, yeah, so I guess the final formula would be, or the final expression of the density function for the exponential of x would be this formula that I've written here times the indicator function on the open interval from 0 to infinity. I guess that would be useful because natural log is only defined from 0 to infinity, and so I guess you need to use that indicator function in order to specify that the function is 0 outside of the interval from 0 to infinity. But yeah, this is the density function, and it looks something like this, I believe. I don't know, I looked it up online. I just plugged into Wolfram Alpha to see what it looks like, and it looks something like this. So of course this is the density function, so if you want to find the probability that the probability of attaining a value between a and b is equal to the integral from a to b of this function. And yeah, I guess it's called the log normal distribution. Well, it involves logs, and it comes from the normal distribution, so maybe that's why it's called that. Also, another thing to note is that when I have minus natural log of x squared, so that's natural log of x times the natural log of x. It's not the natural log of the quantity x squared, because if that were the case, then you could bring the exponent 2 out in front of the natural log, which you're not allowed to do here. But yeah, this is just a simple application of the previous exercise, and there might be a few technicalities that you might have to deal with alpha and beta being extended real values, but it's not really that big of a deal. This is all we need for this problem, and so we are done.